Good afternoon, everyone. My name is Jesse Barker, and I'm a software engineer here at ARM in the graphic software organization, so partially looking after Vulkan and partially looking after prototyping and investigations into some of our future GPU and API features. And I've been doing that kind of thing, I guess, for, gosh, I shouldn't say my outside voice, but the better part of 25 years on various 2D and 3D graphics subsystems. And I have to say that in all that time, one of the coolest things that I've had the opportunity to do and spend time with that really cool group of people that Tom showed the picture of earlier is working on Vulkan for the past couple of years. It's been just a real joy, and it's been pretty awesome. So our talk here today, or at least mine, is really about I think one of the previous presenters, Hans Christian, maybe referred to it as either shape or as sort of the signature. Really, as Tom said in his talk, it's really about the contract between the Vulkan API and SphereV, and being able to provide all of the right data both in and out of the shaders when they expect it. So resources from sort of a very high level are really just these input and output data from a shader. And most of them, in our case, are in memory. Some of them have sort of special little side paths. We'll talk about those very briefly here. I think they've been covered in some of the other talks pretty extensively. And in Vulkan, these shader inputs and outputs are referenced via something that we call descriptors. And I'll go into that shortly. Most of them are sort of, I think of as pretty general purpose, but some of them are really quite specialized. You have things like render targets, which are, they're really just images, but they're kind of special, at least for most people's GPU hardware, they're kind of special, so we call them out and handle them a little bit differently. And the same thing with the way that we feed the actual Vertex input, where again, there's sufficient specialized hardware in a number of GPUs to make it worthwhile us handling this a little bit differently. So some of these that we're talking about, so buffers, these are very much like the same buffers that you had in OpenGL. They're just arrays of data. Images, again, they're just things like textures. Both of these, by the way, on Vulkan can be read and or write depending on how you create them, how you set them up, and what you tell Vulkan you're going to do with them. We have samplers, which are basically parameter sets for looking up data into images and filtering them, computing the coordinates that you're going to use to address the image, and a few other bits of metadata around things like MIP mapping and that sort of thing. And there's one other thing that I'm going to call out explicitly here, and those are input attachments. And Andrew's going to tell you a lot more about why you care about those in his talk. But I call them out here. They're really just a special kind of unfiltered image. So you're dealing with sort of an image that contains, for lack of a better way to put it, raw data. And that does have exposure in OpenGL. If you have used Molly platforms, certainly in OpenGL, yes, and I believe, guys, don't hit me if I'm wrong about this, Imagination supports this also, pixel local storage and frame buffer fetch and those sorts of things. So those were extensions to support this kind of functionality, but they, in Vulkan, we've really brought them to the forefront and made it really a formalized part of the API. And of course, that has sort of full cooperation on the SphereV side as well. And I think Neil actually mentioned some of that a little bit earlier. So those are really what we're talking about when we talk about resources. Descriptors. Well, let's see. So quickly, as Tom mentioned, right, you have a resource like an image, and you've created the image, you've asked it what its memory requirements are, and you've allocated some device memory, and you've bound it to the image. Images in Vulkan can't be sampled from directly. They can't be looked up and filtered directly. We need what we call an image view, which is really just It's really just a continuous view of a sub-resource of an image is what we call it in Vulkan. Really, you decide some section of the image that you're really interested in, and you kind of create a little window into that. And there are some additional things that you can tweak over and above the base image, so you can actually change the format a little bit when you create the view out of the image. That's a little bit different from the base format of the image that you originally created. And so you want to use this in your pipeline. And so, the API requires something that we call a descriptor, which is really, it's just a handle to the object, and some type and some other metadata information that allows the API to make the connection between the actual application resource and making it available to the shader. So, as has been mentioned several times, I take it Michael is right, and the things that we're repeating a lot are actually kind of important. Otherwise, I'm wasting a little bit of air here. But no, I think this is really kind of important. So descriptor sets really are just a way of organizing resources into sort of usable blocks, right? If you want to think of it that way, kind of building blocks like Legos or something like that. In OpenGL, you're probably accustomed to having sort of two ways of doing this on a very fine-grained basis, right? You can either ask the compiler to generate all of your binding locations for you, and then you can ask the API what those are. But we don't generally like reflection very much in Vulkan, so we didn't do that. Or you can explicitly create your own binding locations, and you can tell the API what binding locations you want to use, and then everything else that you do is based on that. But again, it's on a very fine-grained basis. And if you've got, I don't know, let's say it's 100 resources or something like that, they're going to be used with a pipeline, that's kind of cumbersome, and yeah, it's just kind of cumbersome. So in Vulkan, we've allowed the application developer to organize these into sets, and the sets are sort of the nice big package that you can pass handles to and all that kind of stuff. But really, the magic behind descriptor sets, in a sense, is the layout. And the layout is sort of the thing you see described in this table, and I've abbreviated the heck out of it. There's a lot more information in the layout than this, but you determine which binding location you want to use, what type of resource it is that you're going to reference, and what stages of the pipeline are going to consume this resource. So you can actually, as an application developer, you can tell the pipeline, hey, I'm only going to touch this from my Vertex stage, but you don't need to make this available to my fragment stage, and that's okay. It's a little bit of a hint in that the driver can actually sort of ignore that and just make it available everywhere, as long as they're not going to overly constrain the resource mapping for you and make it so that something downstream doesn't work for you. But basically, it's a good way to tell the implementation, this is exactly what I'm doing and how I plan to use all these resources, so please make this as optimal as possible. So the layout, as I say, is sort of like a template from which you can stamp out any number of descriptor sets that look just like that, which is pretty handy if you have, if you really want to keep things simple, for example, you can have basically a very similar or the same, in some cases, overall pipeline layout for your application, and just substitute in new resources and new other things as you go along with all these different pipelines, and you can kind of use the same stuff. And in fact, there's sort of compatibility descriptions within the API that say that, well, if I haven't done anything, if I haven't changed pipelines to something that's incompatible with the last one, my descriptor set bindings live on. So that's also kind of cool. As with command buffers, as Michael was talking about, we have sort of a parent object of a descriptor set, which is the descriptor pool, and it's there to allow the threading model to work. So you have incredibly lightweight threading based on this pool model. You basically use these data structures. Vulkan is very verbose, as I think Tom mentioned, and this is a small example of that. But anyway, you tell the driver, I want you to create a descriptor pool, and I want it to have some number of some type of descriptors. I want 4 samplers, and I want 100 images, and I want, so on. And those get placed in these arrays, and you can tell it. Again, there are some flags Michael referred to the resetting behavior, and the descriptor pools have similar reset logic. You can reset individually or globally, and not globally, but the whole pool, sorry. And then you can also indicate how many descriptor sets you actually expect to be able to create out of this pool. And this is potentially some kind of useful information based on how the driver might internally be allocating this memory. This is one of the sort of only couple of places where Vulkan is actually on the hook for managing a certain amount of its device memory is for the memory that backs these resources. So then you have this pool of some number of each type of descriptors, and so they are tracked separately, and you specify them that way. But then, again, as with the case with command pools, you would have one of these per thread, and that's sort of how you go about managing all of your resource sets in sort of a threaded fashion. You can work on descriptor sets from different pools across different threads, and everything stays sane, and you don't have to take expensive locks in order to do that. Did I go? No, okay. So now we're at the point where we have our descriptor pool, and we have our layouts, and now we can allocate some descriptor sets, and that's actually the easy part, right? You take your layout objects and pass those into the allocate function in the descriptor pool, and the descriptor pool happily returns back some number of descriptor sets based on the number of layouts that you passed in. Now you have this bunch of descriptor sets, and well, you still need to know what to do with them. So the pipeline layout is sort of a layout of layouts. It's the overall signature. It's the thing that ties everything together. And this is, as I say, this is sort of the real instance of that contract between the API and the pipeline shaders that I talked about earlier. And here's a slightly more complicated version of the diagram that we sort of saw on the original descriptor set slide. And unfortunately, I chose really bad colors. But you can see that with the layout qualifiers, you see that so that first uniform buffer you have is in descriptor set 0, and it's binding number 0, and obviously it's a uniform buffer, and we expect to use that in all graphic stages, all graphics operations, and so on. I've intentionally chosen a very simple layout. You can do whatever you want to make this as complicated as you want, but be forewarned that you should test this against anything you care to run on, because your mileage may vary in terms of how well many descriptor sets or descriptor sets with large gaps or things like that. So if you're going to sort of sparsely populate your descriptor sets, there may be penalties for that on some hardware and not others, and you really want to kind of evaluate that for yourself to see how this goes. But having this pipeline layout means that you can set all this up at once, and you know what all your bindings look like ahead of time, and you don't have to do it one little attribute or one little uniform individually at a time. You can do this stuff en masse by binding the descriptor sets to the command buffer. So we have descriptor sets. We know what the overall layout is supposed to be, but we actually don't have resources in the descriptor sets. The descriptor sets are basically empty. They're just slots for them, but they're really empty. So Vulkan provides us with this facility called update descriptor sets, and really that's the way that you fill these things in. And there's sort of two ways that you can populate a descriptor set. The first way is just by writing it directly. So this top data structure, you don't have to look at the whole thing. It's okay. I'm just there for illustration. The first way is basically you pass an array of information about the resources themselves, image views, buffers, buffer views, and samplers, and so on, and you give it a base offset into the descriptor set where you want it to start writing those descriptors and how many you've got, and the driver goes through and takes that information and fills out that section of your descriptor set. Similarly, if you have, let's say you have other descriptor sets, you're going to have, I mentioned the idea that you might use a very similar pipeline layout for a number of different pipelines. One thing you might want to do is copy them. So you can say, well, I've got this descriptor set that kind of mostly has all this stuff that I want to use somewhere else, and you can tell it, okay, by the way, so here's descriptor set A, and I want you to take slots 3 through 26 in that descriptor set and copy them to this new descriptor set that I'm giving you. And the driver will do that. A couple of really important things to note about update descriptor sets. And this ties back into what Michael was talking about with command buffer reuse, which is that you're not allowed to do this while descriptor sets are actually being referenced or used. I forget how we actually say it in the spec. We've gone back and forth on the language a couple of times. But the point is that if you've decided to re-execute a secondary command buffer and you have a descriptor set bound into it, you can't touch it. So that is, again, up to the application to manage that synchronization to make sure that you don't have any uses of that descriptor set in flight when you go to actually update it. And this is maybe one of the reasons why you would possibly want to sort of multi-buffer and multi-thread this sort of operation. The other side of that is that I think to satisfy the use case that Michael was talking about, and I think he was very careful to talk about updating the UBO rather than updating the descriptor set that references the UBO. So you have a little extra level of indirection. So you can, for example, map the memory that backs your uniform buffer object and scribble in new data there and flush that out, and then boom, you're ready to go with the new with the new draw calls of the same command buffer with slightly different uniforms. So that's how I just wanted to illustrate that that's how that would be done, because this can make it look, oh wow, that's really easy. It's not that it's hard, but you have to be careful about how to do it, or you will get yourself into some really weird corner cases and some undefined behavior, I guess we like to call it in Vulkan. Finally, I'm ready to actually do something here. So I've bound a pipeline. Let's say that I've bound a pipeline. We don't care too much about order of operations here, but as I said a minute ago, if you have pipelines which are compatible, you can sort of bind them at will, and your descriptor set bindings don't change. You're fine. But if the pipelines aren't quite compatible, then you can sort of invalidate your descriptor set bindings and maybe not be super aware of it. So let's say we've bound our pipeline already. So we're going to, again, you need to, at some point, you need to have passed enough descriptor sets to the correct binding locations to satisfy the pipeline layout. So Vulkan requires support for a minimum of 4 bound descriptor sets at any given time. So you can have, descriptor sets 0 through 3. The conceptual idea is that you're binding with frequency. So descriptor set 0 is meant to be changed least often, and descriptor set 3 is intended to be changed most often. That doesn't mean you have to do it that way. Feel free just to have descriptor set 0. Everything will still just work. But like I said, if you're kind of mixing and matching and using sort of sections of your pipeline layout and overlapping some of them but not all of them, or your algorithm determines that you need to have some things that change, per object or something like that, then that's how you would sort of accomplish that. And then you also need to tell it what kind of which pipeline to use, because any command buffer has support for a graphics and a compute pipeline at the same time, as long as Michael said, you're outside of a render pass. So you tell it, do I want to use this for graphics and or for compute? Because you can make the descriptor sets compatible for both. So it's possible that you can switch to a compute pipeline that doesn't invalidate a descriptor set. And now you're ready to draw. Oh, I did promise to mention the one thing that was in the pipeline layout that I didn't sort of talk about here, which is push constants. I didn't really talk about them because they're not formal resources in this way. They're kind of a sort of a fast path that's not really sort of a memory-backed object. But those are part of your pipeline layout, and if you define them as part of your pipeline layout, there's another command buffer command called VK command push constants, where you define what the actual push constant data is for that pipeline while you're using that, and you can update the push constants between draws and stuff like that as well. So I did mention I'm not going to talk about render targets because those are special in a whole different way, and I think Andrew's going to talk about them at least a little bit with respect to render passes. But I did promise to talk about Vertex Input and why that's different. And the short answer is that a lot of hardware has fixed function blocks for handling Vertex fetch and Vertex Input. So we made it so that providing that information to Vulkan was done in sort of more of a fixed function way. And but the driver is free. If the driver actually happens to handle this stuff in the shader, the driver is free to basically take the input descriptions I'm going to show you now and turn them into descriptors effectively. But this is what it looks like in the API. So again, very simple sort of GLSL stuff. You have a 3-element position attribute and a 2-element texture coordinate attribute. So in your application code, you might define 2 structures that sort of look like that, and fill out a bunch of host memory and upload them to the GPU and all that kind of good stuff. In Vulkan, it sort of looks a bit more like this. So you have binding descriptions, which are basically how many buffers am I going to bind to the command buffer before I can draw with that pipeline, and then the attribute the attribute description, which is basically what do the attributes within those buffers look like. And so the structures basically allow you to say, well, I've got one buffer that has an array of vec3s in it, and I've got another buffer that has an array of what would they be, uvec2s, I think, in GLSL. And you pass this information into the pipeline at creation time, and then the pipeline when you create the pipeline, it's prepared for 2 vertex buffer bindings, and it expects to find those attributes as they're described there. One other cool thing that we did, which I think is actually pretty similar to the way GL does it, which is I've made this a vec3 just for the purposes of illustration, but in reality, your shader can have a vec4 for position, and you can still pass 3 elements in at the API level, or your vertex buffer can have 3 elements, and you'll get the same old sane 4th element, sort of predefined value of 1. So, or even if it's a vec2 that you've passed into the API, and your shader declares a vec4, you'll get x, y, 0, and 1. So it happily sort of promotes your vector in a sane fashion. So for attribute handling, that's actually kind of a cool thing. And then on top of this, of course, you can bind an index buffer and do draw index, or you can leave it like this and do just a regular draw command. And I think that's it. So questions? Either I made no sense, or everybody really understands this really well. Either way, I'm okay with it. Oh, we are.
Quick one then. Push constants.
Yes, push constants.
Push constants. Am I sort of right in thinking it's essentially a literal in the command buffer?
Is it a literal in the command buffer? I expect so.
Thanks.
Sorry, I don't know how everybody's doing that, so it's kind of hard to answer that question.
Question again?
Oh, the question is, do push constants, when you do a command push constants, does that literally put literals into the command buffer, or is there some other sort of magic going on?
I don't think Vulkan says what cares, right?
Yeah, I mean that's
The coding of them has to go in because it has to happen when you
right.
execute the command buffer.
Yeah, so I mean, they you can I can see different ways to handle this. I don't want to say too much about any particular piece of hardware, but yeah, there could be a bunch of different ways to do it. I mean, you could turn them into, I suppose you could turn them into register loads or something like that. I mean, it really depends on, that's very implementation dependent.
One of those things you say generally, kind of, yeah. Yeah, I think, that injecting neoliterals into the command buffer, I think it's a safe way to think about it, but I think it does come down to being implementation specific. I mean, I believe that we did something like that on NVIDIA hardware. I don't know the specifics of it, but I think it's generally it is it basically hitches a ride with the commands in the command buffer, hence it's on the fast path. But I think, as Jesse says, being specific about it is probably not something we should do.
Anyone else? Okay, so in that case, I'd like to bring up Andrew Garrett, who's going to tell us all about the render pass in Vulkan, or at least I hope so.